All right, so this is the FRC Java Programming Basics meeting. So I'm Brandon. I'm from Team 7028, the Binary Battalion. I am a senior at St. Michael Albertville High School. This is my 4th year in FRC, and I'm the programming lead. And then also presenting is my dad, Andy. He's a programming mentor for 7028. He's a software developer, and this is also his 4th year in FRC. So for FRC Java programming, you're going to have your development environment. That's going to be VS Code, and that's pretty much where all of that stuff is going to be. There's going to be diagnostic tools like Phoenix Tuner and your radio configuration tool, which are going to be able to set up your tools for programming and everything. We're going to talk about the life cycle of the robot, and then we use command-based programming on 7028, and that's probably what is the better one. And we'll talk about command-based programming too a little bit later. So what we need to install in order to get started is WPILib, NI Update Suite, the FRC radio configuration tool, and all of our vendor libraries. So depending on what you have, you'll have to get some vendor libraries, which will be coming up soon. I'll show you what they are. So this is what the WPILib installer is going to look like. So we need to click that select download VS Code first, and it'll run just a little bit, and then that little gray box with the check mark will be able to be clickable. So you'll click that, and then you click execute install, and that'll just make sure that we download VS Code. And then that comes with your Java JDK, Gradle, and all of the WPILib stuff, so you won't need to install anything aside from that. This is what VS Code is going to look like. We're going to have the status bar at the bottom, which I'll show you. That's where messages are going to appear. There's a WPILib button up in the top right corner, which you can see there. And then when you create a project, you can create examples, and I'll show you all that when we get to the demo. So some vendor libraries are CTRE, which is the Talon SRXs, Victor SPXs, Pigeon IMU, Canifier. So those are like motor stuff. Talons and Victors we use all the time on our team. Navex is going to be like your gyro, and Rev Robotics is going to be your Spark Maxes and your color sensors. And you're going to need to make sure that you manage your vendor libraries and get them added to your project before you can use them. So if you're getting issues about your vendor libraries, that's probably what you need to do. All right, so let's go into a VS Code demo. So this is what VS Code is going to look like. Is like this. And to open our command palette, we're going to press Control, Shift, and P all at once. Otherwise, you can press this little WPILib button up here. And we're going to go to this WPILib, create a new project. And for our project type, you will probably use template, but we're going to use example for this. And we're going to use Java. And we were going to use the traditional hatchbot right here. So that's going to open up an example that they've pre-made for us. For our project folder, I'll just put it in somewhere here, just in where? Right here, we'll put it here. We're going to give it a name, so we will call this hatchbot, and our team number is 7028. And that's important that you get your team number in there correctly. And we're going to open it in our current window. So in the bottom right corner, when it loads, you're going to see this right here. And if this is spinning, that means that it's thinking it's doing stuff. So stuff won't work while it's doing that. And it's going to run a build here. So right now I'm just waiting until this says build successful, and that means that it's done. So right there it says build successful, and I should be ready to start programming. So first, I'll show you kind of around here. So you're pretty much going to spend all of your time in this source folder, source main Java, and it's going to bring you to here. So your commands are all going to be within this commands folder. So here's a bunch of commands that they have for us. Subsystems are going to be in here. And then this is going to be your other stuff. So you're going to mainly be in robot container and robot.java. You're never really going to touch this. You're never going to touch this. Yeah, you can pretty much just stay out of the main. And then constants, you'll use that. So robot is where all of your stuff is going to be scheduled, and then this robot container is where all of your stuff is going to be created. So if I go into robot.java and I press some keys here, it's not going to do anything, but right up here, there you can see this little circle in robot.java, and that means that I have unsaved changes. So if I click off of it, right here, that circle is still there, and that circle's not going to go away until I save with Control S. So once I do that, the circle went away. I'll get rid of those. To add a vendor library, you're going to open up your command palette again, and you're going to type manage vendor libraries. You're going to find this one, and then you can install new libraries online or offline, and then it's going to ask you for which ones you want. So I did offline there because I have them all installed. If we want to add Phoenix, we just do that, and it's going to have me run a build afterwards. So anytime you run a build, just give it a minute to let it finish the build before writing stuff. So once I do that, I have my cross-the-road electronics stuff in there. All right, I'm going to pass this off to my dad here. So it'll be just a second.
All right, hello, I'm Andy. I'm going to take it from here and do the other part of the presentation. We switch back to the presentation here real quick. There we go. All right, so when we're programming a robot, we have to think about the life cycle of a robot. What happens when I turn a robot on? How do I make a robot do stuff? So this is where we start. When we first turn a robot on, it's going to execute the code that we want it to do in initialize. So there's a section where we can put the things that we want to do every time the robot turns on. That'll only run one time. So we can do that to set up all of our stuff. Then it will, once initialize is done, it'll immediately start running our disabled code. Our disabled code will run over and over again the whole time the robot is disabled. So the first time we come in there, we probably don't have anything we want to do unless maybe we have some fancy lights on our robot or something that we want to control. But disabled is also where we could make sure all of our robot is stopped and things are reset if we want to do that. Then during a competition, when the competition starts, if you guys are familiar with how FRC works, the first 15 seconds is an autonomous period. So our robot then goes into autonomous mode, and it'll allow us to run our robot autonomously without using user controls. So this is where we'd have our robot, maybe drive a path or deliver some game piece or something. Once autonomous is done, it'll automatically go into teleop, and that's where now we can read user input and run our robot with our Xbox controller or joysticks, and that'll run over and over again, and then our robot goes to disabled when we're done. So our robot could also go straight from autonomous to disabled if our robot emergency stops or we turn it off during the autonomous mode. So this is going to be important because this is how we then write our code, is around these different periods in the life cycle. So some of the robot tools that we use in addition to Visual Studio Code are the driver station. And we've got a picture of the driver station and Shuffleboard up here. The driver station is on the bottom. If you guys are familiar with driving a FRC robot, this is what we would see on the laptop. But you'll notice on the corner there, on the bottom left corner, we have the teleoperated, autonomous, and then they also have a practice and a test mode that we can use too. But we can enable and disable our robot, and then we can run autonomous directly. A practice would run it like we're running it in an FRC competition. It would start our robot disabled, would give us a countdown of a few seconds, then it would run autonomous for 15 seconds and then switch into teleop, and it would run our timer out until our game is over, 2.5 minutes, 3 minutes, whatever it is, and then the robot would become disabled automatically. If you want to just go directly and test your autonomous, you can just do autonomous. If you want to just drive it, you can just choose teleop. So you can do that from the driver station. And then Shuffleboard, in our FRC program, we can put things onto this Shuffleboard window. There's a couple different options for dashboards that you can use. Shuffleboard is the newest one, and I'd recommend it if you don't use one today, don't know anything about which ones to use. And you can put things on there like selecting who your driver is or selecting which teleop you want. But you can also just have it give you state information. Like we have our arm. In this case, it was in the unlock position. We can also put our USB camera live feeds on here. And that can be important depending what you have in your robot. All right. So then command-based programming, this is where we're going to get a little bit more into how we structure a Java program in FRC and how we want to write our code. So command-based programming allows us to break our program into simple pieces that can do tasks. So the main robot program can deal with coordinating the work instead of dealing with the details. So we talked about those different states of a robot. We can deal with that, but when we want to actually drive a robot, that programming will be separate so that we don't get things all intermingled and mixed up. So an example would be if we're going to walk forward 3 feet, let's say, that would be a command that someone might get. You know you need to walk forward, but you don't want to worry about telling your feet to step one in front of the other. You already know how to do that. So the command is working with your feet to do the walking forward. And then we can put commands together into command groups. So it could be, walk forward 3 feet and turn off the light. So walk forward 3 feet is one command, turn off the light is another. We can then put those into a group to say we're going to walk forward. We're going to lift our arm asynchronously while we're walking, place our finger above the switch, and then turn the switch off. That might be a sequence of commands or command groups that we would do. We can do the 2 things at once. We can walk forward while we're lifting the arm, and the command group gives us all of that ability to build up those individual pieces into an autonomous action. Our subsystems then would be used by commands. They encapsulate our basic functionality. So if our commands are what we're going to do, the subsystems are how we're going to do them. But they don't focus on any specific task. So in our example of walking forward, it would know how to move a foot, but it wouldn't know that 2 feet need to move together and how far we're going to walk. Have we gotten there yet? So the subsystem in a robot, we may have a subsystem for our drivetrain. It knows then what motors are on the drivetrain, how to make the drivetrain turn, but it doesn't know how to drive a path, for example. It wouldn't know how to drive forward 3 feet. It just knows how to drive forward straight. So our command would then coordinate, okay, I want you to drive forward straight for 2 feet, then turn 90 degrees, then drive. The subsystem would then know, that means I need to operate these motors in this sequence to be able to do the action that you've asked for. Any questions so far? Then we'll cover the command scheduler a little bit. I'll give you just a moment. If anybody wants to unmute or put anything into the chat, you can do that. All right, so we can move on to the command scheduler. The command scheduler is part of our WPILib framework. And we didn't cover that. The WPILib framework is kind of, you know, we've got Java as a programming language. WPILib is then a framework that we can interact with in Java, but it's built specifically for FRC and building FRC robots. So it provides this command framework for us, and it knows about some of our basic things that come in the kit of parts, but it doesn't necessarily know about our third-party things like the CTRE talons. Those are where our third-party libraries come in, but WPILib is that basic framework. So we would always be using WPILib to write an FRC robot. The command scheduler, then, we use that to run our commands. And it will make sure that 2 commands don't run that use the same subsystem at the same time. So like if I wanted to have 2 commands, one was telling the robot to drive forward, the other was telling the robot to drive backwards, it would take care of the fact that those can't run at the same time. You could either schedule them to say, I want to drive forward, and then I want to drive backwards, but it wouldn't let you do those both at the same time. But it would let you do things at the same time if they use different subsystems. Like we talked about, you could raise an arm while driving forward. It would deal with scheduling those things to happen at the same time. All right, so we can take a look at some code again. We'll use that same example and poke around. Let me see if I can make it a little bit bigger first, because it's, there we go. Probably a little small. There we go. All right, so this was our basic hatchbot example. The hatchbot example that they have in here, I think, was a functioning robot that could do the 2019 game, which was delivering hatches onto hatch panels and then balls behind it. So that's why it's called a hatchbot. So we talked about commands and subsystems. So they have that set up for us already in here. They had a command folder and a subsystem folder. So our drive subsystem in this case is the system that knows how our drivetrain works. And so they put together, they had 4 motors on their sample robot, and they were on these different ports. And so they have then a right motor group and a left motor group. So they probably were talking about a tank drive, essentially, where we've got 2 motors on each side, driving wheels on the 2 sides of the robot. And then we know that because they use this differential drive class. The differential drive class takes care of that for us. It can do some cool stuff. You tell it, these are the motors that I have on the left. These are the motors that I have on the right. And then it can then drive our robot with arcade drive, which would be, we have like an Xbox controller, and the left stick maybe controls our forward backward motion, and then our right stick controls our rotation. So it'll automatically then deal with, okay, if I want to drive forward and rotate, I need to drive the wheels in this configuration. But this class is our drivetrain subsystem that knows about those motors and knows about the differential drive class. It knows that we have encoders on the wheels, so we can tell how they're rotating. And then it provides the ability to, sorry, right here, drive in an arcade fashion. I think it, yep. So then we would take a look at just one of our commands. So we've got a couple commands here. Drive distance is one. So drive distance, we'll see that uses our drive subsystem, and then it knows a distance and a speed that we want to drive. So notice here, it doesn't know anything about motors. It just knows that we have a drive subsystem. And so when we create it, we tell it how far do we want to drive, and we tell it what drive subsystem to use. And then we'll see, we talked about that life cycle of a robot. We have an initialize function that'll run one time when the robot turns on. So we're just going to reset the encoders. We're going to make sure the robot is stopped. And then when it's done running, it's going to stop. And actually, when we start, we're going to start driving. Sorry. So when initialize happens is when our command is initialized, and we're telling it drive forward at our pre-configured speed, and we're not going to rotate. So it drives forward straight. So I misspoke there. Initialize in a command does not run when the robot initializes. It runs when the command initializes. So we had our robot on, in this case, let's say we were in autonomous mode, and we scheduled this command, and we've said, start running this command. That's when this command's initialize method will run. So when the command starts running, it's going to reset the encoders. So we've gone 0 distance. It's going to start driving forward at the speed that we told it to with no rotation. And then commands run our isFinished function over and over again. Just keeps asking us, are you done yet? Are you done yet? Are you done yet? So every time it does that, in our command, we're going to ask the drivetrain, how far have you gone so far? And is that farther than the distance that we were supposed to drive? So once we've driven the distance that we were configured to drive, then we say, yes, we are finished. So the command scheduler knows, okay, I should stop this command now, and it will call our end function. So on end, we stop the robot. So when that command is scheduled, we drive forward for the pre-configured time, and then we stop the robot. So one thing to mention is that each subsystem can have a default command. So that means if no other command is running for that subsystem, this command will run. So a really common one where we would use that is in our drive subsystem. If I'm not doing anything with my drive system in the code, I probably want my driver to be able to drive the robot. So we can see here we've got in our robot container is where we instantiate everything. We have our drive subsystem here is where we create it. And then in our setup method, we set a default command for that drivetrain subsystem. And the default command is this one that they, in the example, called default drive. And so it takes the drive subsystem and then reads the Xbox controller Y and X, like we talked about. The Y would be the up and down motion on your left hand. The X would be the right and left motion on your right hand. And we give that information to this default drive command. And this command is then the one that runs over and over again when nothing else is running on that subsystem. So here in its execute method, which would run over and over again, it just reads the position of the controller sticks and then calls that arcade drive function. Any questions so far? Then we'll look at a complex autonomous sequence next. Just pause for a second to see if anybody wants to unmute or put anything into the chat. All right. So complex autonomous is done. I'm going to close this so we can see a little bit more. There we go. Complex autonomous sequences are done by creating those command groups like we talked about, where we said if we want to be able to drive a distance, we want to be able to let go of a hatch panel, and then we want to drive a distance in this example. So they drive forward, release a hatch, and then drive backwards. So this would be a function that would, drive the robot forward, let go of the hatch panel because it's now stuck onto the rocket, and then drive backwards. So we do that by creating a sequential command group. A sequential command group means, we're going to run things in sequence. We're going to run one command. When that one's done, we're going to run the next command. Versus we can run a parallel command group, which would say run these two commands at the same time. That's not what we want to do here, because we want to drive forward, release, and then drive backwards. We don't want to drive forward and release the hatch panel at the same time. We drop it on the ground. So we can create a sequential command group, and then in its constructor, we can call its add commands function and just give it the commands that we want it to run in a sequence. So we use that drive distance command that we looked at before, where we say we want to drive forward this pre-configured distance. We want to do it at this pre-configured speed. And here's our drive subsystem that we're going to require. So this will drive it forward using that code that we looked at earlier. Then it would release the hatch panel using the hatch subsystem. So we don't, in this case, we don't even know how the hatch subsystem works, and we don't care. We just know the hatch system has the ability to release, and we have a command already that knows how to make that happen. We put that after driving forward, and then we're going to drive backwards. We probably are also giving our drive distance and the distance that we want to drive, but we're saying instead of driving forward at that pre-configured speed, we're going to drive backwards at that pre-configured speed. So then when we would schedule this with the command scheduler, our robot would do those functions. And when it was done, it would return Xbox controller control to the user because that's the default command. All right. So then we'll talk a little bit about some of the diagnostic tools that are handy for a programmer. A lot of times a new programmer misses out on a lot of these tools that are available, and they can be really helpful to figure out what's happening with your robot. So I was probably 2 years in before I realized there was a log viewer. The log viewer allows you to be able to look at your robot, while you're bench testing it and running it in your shop, but you can also go back after a competition event and look in the log viewer to see what happened. So it'll give you a lot of information, the power draw on the PDP ports. So you could see, how much power your motors were drawing. Maybe when something happened, it malfunctioned your robot, you were trying to figure out what went wrong. You can go back and look in here and realize, oh, I meant to be driving forward at full speed and somehow it was driving backwards. And so you can then see what the robot was actually doing. You can see a history of the voltage on your robot battery. So we had some trouble with our batteries not lasting an entire match. We could then look at what happened in our events and try to narrow down which batteries were the ones that were giving us trouble, because we could see that their voltage was dropping. It'll actually give you a little indicator bar if there's a brownout. A brownout is when the voltage drops so low that in order to preserve your RoboRio, which is the brain of your robot, to prevent that from shutting down, it'll shut down your peripherals. So your motors will stop to preserve power for your RoboRio to work. Well, when brownouts happen, bad things happen with the function of your robot. It maybe is stuttering while you're trying to drive, or it maybe drops the game piece that it was trying to hold on to. So it's a good thing to go back and look and see if you had any brownouts. And if you did, understand why you're drawing too much power and get those corrected. You can also see if the radio disconnects. Common reason why that might happen is the location of your radio, or maybe your connections are bad. So if you're having trouble with your robot not behaving correctly, you can see maybe my radio disconnected. But for programmers, you can also see program errors and other messages that you put in to your code using system out functions. So something we do sometimes is put a system out message to print to the terminal, maybe when a command starts and when a command ends. And you could go back into your log then and see at this time, this command started and it ended. Maybe you were expecting something to happen in your autonomous function and somehow your first command never finished, so your second one didn't run. You could put some messages in there to help you understand what was happening, as well as any errors that happened that were unexpected. Those would get logged and you can view them here. Shuffleboard is that other utility that we already talked about that we had the picture of above the driver station. In our code, we can put all kinds of widgets on Shuffleboard, and you can use that both to see what's happening as well as set parameters that you want to use in your program. The outline viewer is something new that I didn't realize existed. There's the Shuffleboard uses network tables, and so do a lot of our other peripherals. So if you have a Limelight, for example, that gives you vision capability, it communicates with the RoboRio using what's called network tables. The outline viewer, we can open that on our laptop and we can look at what's going back and forth in the network tables, and we can even edit it. So it's handy if you have components that talk to each other over network tables, you can look at that information. You probably wouldn't want to do that during a competition, but you could do that in your shop when you're looking at what the peripherals are doing to each other. And then Phoenix Tuner is the last one that we have a picture of that on the bottom right there. That's provided by CTRE, they're across the road electronics. You would use that if you had like Victor XPXs, Talon SRXs, or Falcons, but you also would probably use it even if you were just using the kit of parts, because the kit of parts has the PCM and the VRM and the PDP. Those are all components that come in the kit of parts that are on every robot. And this is the utility that you use to update the firmware. So the software that's built into those, into that hardware. Usually when you get it out of the box, it won't have the latest version on it. And FRC will require that you have a certain minimum version for it to work in a certain year. So we can see in this screenshot all of the components that we had plugged in, and then it tells us what type of hardware they are and what firmware version they have. Then we can select them and select the version that we want to install, and then we can flash that. So this comes with our third-party library install for the CTRE components. You can also test and configure motor controllers using this. They're continuing to add more functionality to this tool every year. And last year we ended up using it a fair amount. There's a plot tab and a self-test tab. So you can have essentially no code on your robot, just this Phoenix Tuner installed on your robot. And you can go to the self-test tab and you can select a motor controller and say, I want to run it at this speed, and it'll run it. So we did that, here and there to figure out, did we have a wiring problem? What was going on? And then the plot is also a very helpful tab, which I wish I had a picture of, but that'll show you, you would select a given motor controller and it'll show you what it's doing right now. Is it outputting voltage? What is the current encoder position? And then it maps it over time. So one of the things that we have to do when we install encoders is make sure the encoders are in phase with the motors. So when our motor runs forward, our encoder values go up. The plot makes that really easy to see. You open up the plot, you make sure that you can see your encoder and the output, and you run the motor. And if those two lines go up together, it's right. If one line goes up and the other line goes down, then you're out of phase and you need to flip those around. Yeah, you can also set your controller IDs in here. So each device type has to have a unique ID. So here we have all these Talon SRXs. These are motor controllers. These all have to have separate IDs. So here's how you set them in this tool. You can also select one and then click the little blink button, and there's a light on the controller and it'll blink that one. So during build season, usually we don't get our robot as a programmer until week 5, maybe week 4. They hand it to us and say, now make it run. Well, we've written code hoping that it's going to work, but the first thing we have to do is go in and configure all of our motor controllers for the IDs that we put into our code. And this is the tool that we use to do that. We can identify all of the motor controllers, set the IDs right, and you can even rename them in here. So like this one here, we have a Talon 0 right, Talon 1 left. You could rename them all to be something that's meaningful to you. So when you come back in here into Phoenix Tuner, you can identify them without having to blink them. Down here is the installation path for the log viewer. You don't get a shortcut on the desktop for that by default. So you have to go and locate that tool. And the outline viewer is also in that same folder. All right, so that's everything we wanted to cover. We have a few links here. The FRC programming documentation is on this docs.wpilib.org. They have really great documentation. Last year, they went to a whole new site for how the documentation is laid out, and there's a lot more information there. It walks you through all these tools that we did, walks you through how to do a lot of different functions. The CTRE Phoenix is at that location. They've got great documentation too. It's in the same kind of structure as the FRC programming. If you want to install encoders, do anything with those tools, they give you lots of information and examples how to do that. The SparkMaxes link is there if you use those, and the NavX link is there as well. Last year's color sensor had a separate link. It's a little harder to find. I didn't put that one on here, but and then that QR code down there would give you a link directly to this presentation if you want to look at that later.